In today's video, we're going to be talking about trigonometric identities. First off, by definition, what a trigonometric identity is it's an equation involving trig functions that is true for all values. So it's kind of like a formula, if you want to think of it like that. All values for which every expression in the equation is defined. Of course, it does have to be defined before we can use it, and we'll talk more about that in a second. The identities help us to do these things. We can evaluate functions with identity, we can simplify expressions, we can prove identities, and we can also solve equations. We're going to need these identities for lots of different things, so it's very important that at least these fundamental identities that we commit to memory. And the first one of those being that the tangent of a function, or the tangent, of an angle will always equal the sine over the cosine. These are called the quotient identities. And vice versa, the cotangent will be the cosine over sine. So what that tells us is anywhere that we have a sine over cosine in a problem, we can replace it with tangent. Anywhere we have tangent, we can replace with sine over cosine. They're the same thing. They're one and the same. A proof for that, you can think of it like this. What if you wanted to find the tangent of 30 degrees? Maybe you haven't memorized your unit circle like you should have. Well, to find tangent of 30, we know that tangent is the same thing as sine divided by cosine of that angle. And we can evaluate that. The sine of 30 is a half. The cosine of 30 is root 3 over 2. Flip and multiply. The 2's cancel. Leaves me with 1 over root 3. Rationalize that. That's root 3 over 3. And we know that that is true, that the tangent of 30 is root 3 over 3. And that's always true. So tangent can be replaced with sine over cosine or vice versa. Then you have your reciprocal identities. We know that, oh, by the way, notice that they've tacked on cosine can't be 0, sine can't be 0. Well, we know that we can't divide by 0, so that's the reason. This will only work if we're for sure that cosine isn't 0 here. So we can't use this to find the tangent of 0, because the tangent of 0, that'd be the sine of 0 over the cosine of 0. Well, you can't divide by 0. The cosine, we can find that. We can't find the tangent of 90. Tangent of 90 is the sine of 90 over the cosine of 90. Well, the cosine of 90 is 0. So at 90 degrees, we have something actually 1 over 0, which is undefined. So that's the reason we can't use this formula when cosine is equal to 0. Our reciprocal identities, we know that sine is 1 over cosecant. Cosecant is 1 over sine. They're reciprocals of each other. And those follow as well for secant and cosine are reciprocals. Tangent and cotangent are also reciprocals. Then finally, you have some of the most important identities there are out there. You have what's called the Pythagorean identities. And let me show you actually where this Pythagorean identity come from. We know that our basic unit circle that we talked about earlier this chapter, the unit circle, the equation for a unit circle is x squared plus y squared equals 1. But we also reminder that each point on this unit circle corresponded with the cosine and the sine values of the angle where the point where the angle crossed the unit circle. Well, if a cosine value is an x value and a sine value is a y value, if we were to actually replace x and y with cosine and sine, we have this formula. We have this identity, cosine squared plus sine squared is equal to 1. What does that mean? Anywhere we have cosine squared plus sine squared or sine squared plus cosine squared, we can actually take it out and we can replace it with the number 1 because they are one and the same. They are equal to each other. Something else I do want to point out there that I want to remind you if you've never seen this, what cosine squared means is the cosine of the angle in parentheses all squared. That you would actually evaluate this cosine of this angle. We don't put the squared on the end because it's not the angle being squared, but it's actually the entire function being squared. So that's the reason it's written the way that it is. And then that follows with 2 more Pythagorean identities that I actually want to derive for you really quick and show you that if you can remember cosine squared plus sine squared equals 1, you can actually get these other 2 from that. So let me write this down, cosine squared plus sine squared, and I'm going to do it without the actual theta. I'm just going to leave it off to derive these for you. And if I were to go through and divide everything by another cosine squared, I want to show you what you actually get here. Cosine squared divided by itself would be a 1 plus. Reminder of what we said sine over cosine was a while ago. If sine over cosine is right here, is tangent, so sine squared over cosine squared would be a tangent squared. 1 over cosine, we also talked about that one just a minute ago. 1 over cosine is right here. That would be a secant. So you have 1 plus tangent squared equals secant squared. So that would be this identity. Tan squared plus 1 is equal to secant squared. And that means that you can actually find that last identity here by doing the exact same thing, except for instead of dividing by cosine squared, we're going to go through and we're going to take every piece of this. Let me get that erased right there. And if you were to go through and divide every piece by sine squared now, and look what happens to your original Pythagorean identity. Cosine over sine, that's right here. That's cotangent. So cotangent squared plus sine squared over sine squared, anything divided by itself is 1. And then finally, 1 over sine is right here. That is cosecant squared. So cotangent squared plus 1 or 1 plus cotangent squared is cosecant squared. So if you can just remember that sine squared plus cosine squared is 1, you can derive the other two. Now, actually using these identities, here's how we're going to use them. Notice it says find the exact value of the sine if cosine is negative 4/7. And then they tell you what quadrant you're in. They say that this angle theta is between, reminder that pi over 2, that's 180 divided by 2, we're between 90 degrees. I'm going to write it over here that your angle is somewhere, well, it has parentheses instead of brackets. Your angle is somewhere between 90 degrees and 180 degrees. That means that you are in quadrant 2. Now, let me explain. The whole purpose of this is simply to tell you if your answer is going to be positive or negative, because we know back from unit circle, all students take calculus, that if you're in the second quadrant, sine is a positive value. We know that in the second quadrant, sine is all that's positive. Cosine and tangent would be negative, as you see here. Cosine is negative, tangent would be negative, but our sine value is going to be positive here. So that's going to tell us if our answer is positive or negative. That's all that does. So here we go. Here's how we're going to do it. If I've got cosine and I'm looking for sine, reminder, you've got to find an identity that somehow relates sine and cosine. This is the only one that involves only sine and cosine. This one involves actually sine, cosine, and tangent, so let's not use this. Let me pause it and erase all this for just a second. Okay, so if we know that cosine squared of an angle plus the sine of the angle squared is equal to 1, we can use that fact, plug in our cosine value here, and it's going to tell us what our sine value is equal to. So here we go. If the cosine is negative 4/7, take and plug that in for the cosine, and we have negative 4/7 squared plus sine squared is equal to 1, and we have a basic equation. Negative 4/7 squared is 16 over 49. To square a fraction, here's all you have to do. That'd be negative 4 over 7 times negative 4 over 7. We know any negative number squared is positive. And then to actually square it, just square the top and square the bottom. Multiply the two bottoms, multiply the two tops. Plus sine squared is equal to 1. To solve this equation, we've got to move 16 over 49 to the other side. I want to remind you that this one whole is 49 out of 49. It's 5 out of 5. It's 6 out of 6. It's 7 out of 7. So when you subtract 16 out of 49 from 49 out of 49, you're left with sine squared is equal to, I believe that would be 33 out of 49. And then our very last step to figure out what sine is, to undo a square back from quadratic equations, you have to square root the other side. But you've got to be careful, if you remember from those days, that when you square root the other side, you cannot forget the plus minus. So you have positive negative 43 out of 99. In the same way that you could just square the top and bottom, you can do the same thing with square roots. In order to find the square root of 33 over 49, you can simply do the square root of the top and the square root of the bottom. So you get positive and negative root 33 over 7. Now again, to actually find the answer, reminder that we're in the second quadrant where sine is always positive. So here our answer says it's either positive or negative. that means that we can throw out our negative answer, and our answer is going to be just simply root 30. Now, there is another way of working these problems, and I do want to give you options. I want you to know both methods of this, because this second method might be a little bit faster, and on the ACT, there's a good possibility you might use this method instead. So what you can do is draw you an XY axis. We know that our angle is somewhere in the second quadrant. So what I want you to do is draw a second quadrant angle over here. It doesn't matter where, just make sure it's in the second quadrant. So there you go. There's your angle. And I know that the cosine of my angle is -4/7. So what I'm going to do, instead of using that angle theta, I'm going to use my reference angle, because I know that if based on positives, negatives, as long as I put my reference angle in the right spot, that sine, cosine, or tangent value is going to be the same. The only difference might be the positive, negative. So what I'm going to do, I'm going to construct a triangle with this reference angle that has a cosine of -4/7. Ignore the negative, and just a reminder that cosine from the whole SOHCAHTOA is adjacent over hypotenuse. So if the cosine is 4/7, then that means my adjacent side is 4 and my hypotenuse is 7. And I'm going to construct myself a little right triangle here. And what I'm going to do is I'm going to use the Pythagorean theorem, a squared plus b squared equals c squared, or 16 plus b squared equals 49, to figure out what this missing side is. Subtract 16 gives me b squared is 33, which means my missing side is root 33. Now look how easy this is. We're looking for the sine. Sine is opposite over hypotenuse, so root 33/7. The only thing that you've got to remember is, okay, now you have to figure out, since you're in the second quadrant, is my sine positive or negative? It is positive, so that gives you the exact same answer. Next one, we're given the cotangent, we're looking for the cosine. So let's see if we can find one that relates cotangent directly with cosine. And I don't see one. Cotangent with cosine, I can do cotangent to tangent. I can do cotangent to cosecant. And that might be an option there by using that Pythagorean identity. I could do tangent to secant, and I know that secant is the reciprocal of cosine. So you've got several different options here, and honestly, it doesn't matter which one that you pick as long as you make it to the right spot. So I'm going to do this. I know that since cotangent is 2/5, reminder that cotangent and, where's it at? Right here, tangent. Either one of these says that cotangent and tangent are reciprocals of each other. So since cotangent is 2/5, I can say that the tangent of the angle would be 5/2. And now that I know the tangent is 5/2, I know that tan squared plus 1 is secant squared. So let's go that route. Let me write that down. Tangent squared of an angle plus 1 is equal to the secant squared of the angle. Since the tangent is 5/2, I can plug that in here and say 5/2 squared plus 1 is equal to secant squared. 5/2 times 5/2 is 25/4 plus 1. And I'm going to go ahead and write that as a common denominator is equal to secant squared. Add those together gives me 29/4 is equal to secant squared. To undo a square, we're going to square root. So that's going to give me the square root of 29 over the square root of 4 is equal to secant. So now I have the secant, but you've got to be careful because to undo a square, you've got to do plus and minus. So now we've got to figure out in that quadrant, well, where are we? We're between 180 and 270. So that means that we're in quadrant 3. We've got to figure out, would secant be positive or would secant be negative? And I'm going to be honest with you, I don't have secant and cotangent memorized. I have sine, cosine, and tangent memorized because I know that all students take calculus. Tangent, out of those three, is the only thing that's positive. So that means sine and cosine are both negative. And since sine is negative, or excuse me, since cosine is negative, because cosine and secant are reciprocals, since cosine is negative, then that means secant is negative. So let's do away with our positive sign. And we have that the secant is negative root 29 over 2. So there's your secant, but I'm looking for cosine. So if you have secant and you're looking for cosine, all you have to do is flip it. So the cosine of the angle would be negative 2 over root 29. Then you do have to rationalize that. So that means that cosine of the angle would be negative, multiply top and bottom by root 29, would be 2 root 29 over 29. And that is your final answer. Okay, the next problem gives you cosecant. And again, I know that we probably aren't comfortable working with cosecant. So if the first step that you would like to do is, okay, since I know cosecant, then I know sine. You just flip it. So really you can either use a cosecant value or the sine value, but we're asked to find the tangent value. So let's try to find a relationship between tangent and cosecant. So let me go up here. Let me erase some of these. Tangent and cosecant. I know cosecant here is related to cotangent, and that would be very easy to change cotangent to tangent. That's one option, and that's probably going to be our best option. So let's write that down. Cotangent squared plus 1. The cotangent squared of an angle plus 1 is equal to the cosecant squared of an angle. And again, that's your third Pythagorean identity there. The cotangent squared of an angle plus 1 is equal to cosecant squared of an angle. So we're given the cosecant squared. So this one should be fairly simple. So I now have, let me scroll up a little bit, the cotangent squared of an angle plus 1 equals, the cosecant is negative 2. So I'm going to go ahead and square that as I plug it in. Negative 2 squared is 4. Move your 1 over by subtracting, gives you the cotangent squared is equal to 3. So therefore, the cotangent of that angle, in order to get rid of a square, we're going to do plus and minus the square root. Now we ask ourselves, what quadrant are we in? This is 270 and 360. If you're between 270 and 360, that would be a fourth quadrant angle. So if you're in the fourth quadrant, okay, cotangent and tangent are reciprocal, so all students take calculus. Cosine is the only thing positive. So therefore, tangent and cotangent would be negative. So we can do away with our plus minus, and we can go ahead and put our minus there. And now that we do have cotangent, we know that in order to find tangent, all we have to do is take that root 3 over 1 and flip it to 1 over root 3. Rationalize it would be a negative root 3 over 3, and that would be your final answer. I do want to remind you there is a second way of working that. In every one of those problems, if you'd rather work it like this, I do want you to get comfortable using identities, but I do want to remind you of this as well. Since the cosecant was negative 2, that means the sine was 1/2 or negative 1/2. You're in the fourth quadrant, so you'd come down here and draw yourself a fourth quadrant angle. Construct a triangle. I accidentally erased it. Construct yourself a triangle using your reference angle. Always has to be your reference angle, so you always have to draw that to the x-axis. Since we know the sine is 1/2, sine is opposite over hypotenuse. In order to find that missing side, all you've got to do is a squared plus b squared is equal to c squared. That means that a squared plus 1 equals 4. Move the 1 over. That means a squared is 3. So that means a is the square root of 3. And you can put plus and minus there. Really, the plus minus won't matter because what's going to take care of that is the fact that all students take calculus. Since we're dealing with a fourth quadrant, when we go to find the tangent, we know it's going to be negative, and that's what you see here. The tangent was negative. So in order to find the tangent, you're going to do tangent is equal to opposite. Here's your angle. Opposite over adjacent, which is 1 over root 3, and we knew that it was negative. And then once you rationalize that, you get the exact same answer, probably a little bit quicker. Okay, another way that we can use these trig identity is to simplify expressions. To simplify a trigonometric expression means to rewrite it as a numerical expression or in terms of a single. Instead of having two different trig functions here, trying to write it as a single trig function, as just sines or just cosines or just cotangents or cosecants or whatever, if at all possible. Use the identities to help you simplify the expressions below. Sine times secant. And my advice for you, what I like to do first, is if you're dealing with sines and secants or sines and cotangents, try to write everything in terms of sines and cosines. It makes these problems a little bit easier. So what I'm going to do is I'm going to leave the sine. I'm going to put it over 1. And I'm multiplying by secant, which I know that from the reciprocal identities, that secant up here, let me erase these that I drew. Secant up here is the same thing as 1 over cosine because they're reciprocals of each other. So what I can do is I can rewrite secant as 1 over cosine. So when I multiply these together, and I'm looking ahead, these are going to take a little bit of practice because I looked ahead and I saw where I was headed with this. If you multiply the tops and bottoms, look what you get. You get sine over cosine, which is still a problem because I still have two different functions there. But wait a minute. Your first quotient rule or your quotient identities said that sine over cosine, if you scroll back up, sine over cosine is the same thing as tangent. So we can clean that up one more time and say that that is equal to the tangent. So therefore, the sine times the secant is the same thing as the tangent. Second problem. Again, instead of tangents and cosines, let's try to write those tangents in terms of sines and cosines. So I know that tangent, from what I just did, tangent is the same thing as sine over cosine. And I've got to multiply that by cosine. And what happens? The cosines cancel. And you get just sine. So we've written that as a single function. Now, also advice, anytime you start seeing squares, start thinking Pythagorean because we know that sine squared plus cosine squared is equal to 1. So anytime you see those squareds, we're going to be dealing more than likely with one of these three functions. So again, this is kind of trial by fire, trial and error. You're trying to plug something in. And if it works, it works. If it doesn't work, we go back and we try to plug something else in. So we're dealing with secant squares and tangent squares. So secant squares and tangent squared. So obviously we're dealing here. Tan squared plus 1 is equal to secant squared. So let me write that down. Tan squared plus 1 is equal to secant squared. Now, you'll notice a lot of times that I'll leave the angle off. It's no big deal. I'll leave the angle off just because I know that there's implied to be an angle there. So it's no big deal if you leave it off. Now, sometimes, let me show you what you have to do. Sometimes in order to get a trig identity to fit, you're going to have to manipulate it. And the same way that if you had like the Pythagorean theorem, you can manipulate that Pythagorean theorem back from algebra 1. What if I want to move the a squared over here? That's fine. Mark it out, and a squared turns into minus a squared. The same way if you're doing x plus 3 equals 7. What if you want to move plus 3 to the other side? You minus 3. You do the opposite operations. The same thing applies here. If you notice what's in parentheses here, secant squared minus tangent squared, what if I took this identity, marked tangent squared out, and moved it to the other side? It becomes a minus tangent squared. And look what secant squared minus tangent squared is equal to 1. So since secant squared minus tangent squared is 1, I can take and I can replace secant squared minus tangent squared with 1. So this expression is now 2 times 1, which is 2. But we've really cleaned that one up. The next one, we know the fact that cosine squared plus sine squared, the most fundamental Pythagorean identity, we know that that's equal to 1. But what does cosine squared minus sine squared equal? A little bit tougher here. So what we can do, one thing we can try is kind of what we did a while ago. Can we move these around to turn this into a cosine squared minus sine squared? Well, you move over to here and you have cosine squared is 1 minus sine squared. If you move the cosine squared, you have sine squared equals 1 minus cosine squared. So you really can't turn this into cosine squared minus sine squared. So we're going to have to think of another option. And there's actually going to be two different answers we could go with here. And let's do this. First way we could try this, let's move the sine squared over. And I know that cosine squared is 1 minus sine squared. So what you can do to clean this up, you can take the cosine squared and you can replace it with 1 minus sine squared. And that turns this into 1 minus sine squared. And you can leave the theta in there if you want to, minus sine squared. So you have, these are actually like terms now. That's kind of like 1 minus x squared minus x squared. You could rewrite that as 1 minus 2 sine squared. So that's one way that you could clean that up. Let me change colors here. You could also say, well, let's take our first equation up here, our Pythagorean identity. What if you move the cosine squared over? You have sine squared is actually the same thing as 1 minus cosine squared. And I'm leaving my thetas off. So take your original problem and take out sine squared and replace it with 1 minus cosine squared. So then you have cosine squared. Now you've got to be careful with this one though. Minus sine squared is in parentheses because you're subtracting it. So that'd be 1 minus cosine squared. So that turns into cosine squared. You can write the theta right now, or you can leave it off. Minus 1, then minus minus would be plus cosine squared. You can combine like terms. Cosine squared plus cosine squared would be 2 cosine squareds minus 1. So that's another way you can leave it. So what we've done is we've simplified. We used to have cosine squareds and sine squareds. Now we have either just sine squareds or just cosine squareds. Okay, next one. We have sine times cosine divided by tangent. So I know that already I can turn that tangent. We can do sine times cosine divided by, tangent is the same thing as sine over cosine. Now to divide, you have sine times cosine, and I'm going to put that over 1. To divide two fractions, you take the second one, which is on bottom here, you flip it and you multiply. So that'll be times cosine over sine. Again, to divide fractions, you flip the second one and you multiply. And the signs will cancel. And it leaves you with cosine times cosine, which is cosine to the second power. Next up, you have 2 minus 2 sine squared over cosine. Now this one, now we're getting really challenging with these because this doesn't fit anything. 2 minus 2 sine squared, a couple of different ways you can do this. I'm going to show you the hardest way to begin with. I know that sine squared plus cosine squared equals 1. Which means I can take, to replace this sine squared with cosine stuff, I can move the cosine stuff over, and that sine squared is equal to 1 minus cosine squared. So now, and again, this is one method of doing it. I'll show you another one after we finish. So now on top I have 2 minus 2 parentheses, to where sine squared I'm now going to replace with 1 minus cosine squared. Now, why would I even want to do that? Because I have cosines on bottom. It'd be nice to have cosines on top and bottom. Now, let's use some basic algebra to clean this up. 2 and then negative 2 times 1 would be negative 2. Negative 2 times negative cosine squared would be a positive 2 cosine squareds over cosine. 2 minus 2, they cancel. And that leaves me with 2 cosine squareds on top and 1 cosine on bottom. And if the cosine squareds are confusing you, imagine if it was like 2x squared over x. It's the exact same thing. You're going to use your rules of exponents. There's 2 x's on top, 1 x on bottom. They cancel and leaves you with 1 on top. There's 2 cosines on top. There's 1 on bottom. They cancel, and I'm going to put my theta back in there, and it leaves you with a single cosine on top. Now, I told you there's another way of working that, and I noticed this as I was writing this down, that you could also take and you could factor the top. You could factor out a 2, and you're left with 1 minus sine squared on top and cosine on bottom. And the other way of working that is if you took this and you manipulated it in this way now. 1 minus sine squared, well, wait a minute. I can move the sine squared over, and I could find out that cosine squared is equal to 1 minus sine squared. So you could take that 1 minus sine squared then, and you could replace it with cosine squared, and it actually takes you straight to here. So you can work that either way. Okay, next up again, I've got some secants. I don't like working with secants, so what I'm going to do is everywhere I have a secant, I'm going to replace it with 1 over cosine because that's its reciprocal. So I've got 1 over cosine times sine squared, and I'm just going to put that over 1 divided by 1 plus 1 over cosine. Now this one's going to be a little bit tougher. Be a pretty tough problem. Because we're going to have to go back and talk about some rational expressions about how can you add these together? How can you multiply these together? Now, on multiplication, that's pretty easy. On top, to multiply 1 over cosine times sine squared, you multiply tops, multiply bottoms, and that gives you sine squared on top, and it gives you cosine on bottom. So that part was easy. Now, on bottom, though, how can you add 1 plus 1 over cosine? What you're going to have to do here is you're going to have to find common denominators. Let me do it in a different color here. So I've got 1. That's the same thing as 1 over 1 plus 1 over cosine. Well, I've got a cosine on bottom here. I really want a cosine on bottom here, so I can't add these. So the way you do that is you multiply top and bottom by cosine. So now these can be added by cosine plus 1 on top. We leave as cosine plus 1. On bottom, we have our common denominator, which was cosine. So I'm going to replace 1 plus 1 over cosine with cosine plus 1 over cosine. So now it looks like actually worse than what I started with now, but it's not too bad from here on out. Now we've got a single fraction on top and a single fraction on bottom. We've got to divide these two. That's what this bar means. So I've got to do the top divided by bottom. To divide two fractions, you take the second fraction, you flip it, and you multiply. And you see here what's going to happen when I flip and multiply. My cosines actually cancel. And I'm left with sine squared on top and a cosine plus 1 on bottom. Now, again, from here on out, because I would really like to simplify this down to where I've just got sines or I've just got cosines, I don't have a mixture. Now, this next part is going to be a trick that is going to be, the more you work these, the more comfortable you're going to get with it. But before we go any further, I want to remind you of something. And this might seem so unrelated, but let me remind you of some factoring rules. X squared minus 4, this is what's called difference of squares. And difference of squares always factors into what we call conjugates. X times x gives me my x squared, and a positive 2 times a negative 2 would give me my minus 4. And you might be thinking, well, how is that even related to any of this? Well, let's take our Pythagorean identity, the most popular, the most basic one, and that was cosine squared plus sine squared is equal to 1. And I want to do this. I want to take the cosine squared. You can do either one, but let's move the other one to the other side. Let's take cosine squared and move it over and write that as 1 minus cosine squared. And I want you to look at this. And I want you to compare it to this. Because 1 minus cosine squared is actually difference of squares. So that could be factored into sine squared is equal to 2 sets of parentheses. 1 times 1 gives you the 1, and then minus cosine squared will be a plus cosine and a minus cosine. So what I can actually do with that, why is that even important? Knowing that is because I noticed on bottom I had a 1 plus cosine. And I noticed I had a sine squared on top. So what I'm going to do is I'm going to take and I'm going to replace, I'm going to come down here, and I'm going to replace the top, that sine squared, I'm going to replace it with 1 minus cosine squared, which what I did there is I took my Pythagorean identity and I solved it for sine squared by moving the cosine squared over, and I replaced it with 1 minus cosine squared. And on bottom I have cosine plus 1. And I want to remind you that, again, that top can factor, and it can factor into, close this stuff out. The top can factor into 1 plus cosine times 1 minus cosine over, and on bottom we have cosine plus 1, which we understand is the exact same thing. And it's quit writing on me. So therefore, since cosine plus 1 and 1 plus cosine is the same thing, we are left with 1 minus cosine. And you can put your theta back in there for a final answer. Okay, last one of these. Let me erase some of this stuff. I already noticed as I'm looking at this, we're probably going to use our original Pythagorean identity because I see sine squares and cosine squares, and we know that sine squared plus cosine squared is equal to 1. So more than likely, we're going to replace it with that original one. And I noticed something else too, and a strategy that I always look for is I notice that I have two terms, and both of those terms have sine squareds in them. So sometimes you want to start these problems out by factoring. So I would really like to factor a sine squared out of these two, and I'm left with a 1 because sine squared times 1 is sine squared, minus sine squared times what gives you this term would be cosine squared. A couple of different ways you can do this, and I think the easiest way is going to be this. Since you have a 1 minus cosine squared in parentheses, I know that cosine squared plus 1, or excuse me, plus sine squared, get ahead of myself, is equal to 1. So if you move this cosine squared over, you know that 1 minus cosine squared is equal to sine squared. So here's 1 minus cosine squared. I can just replace that with sine squared. In the same way, what if this was x squared times x squared? That'd be x to the fourth. Well, sine squared times sine squared would be sine to the fourth. And you can put your theta back in there, and you are done with that. Now, before I stop, I do want to remind you that this is not the only way to work these. There's more than one way to work these problems. Maybe you used a different strategy here. Maybe you took and replaced sine squared with 1 minus cosine squared. That's fine. And sometimes you're going to clean it up and it's going to look different in the end. And why does it look different? Because there's so many different identities that we can use here. And here's the funny part about it. This is just a tip of the iceberg. There's hundreds of thousands of identities out there, but these are the basic ones. So there's other identities that we're going to learn throughout the next few lessons that you can actually use to simplify these, that you can clean them up. So just because your answer doesn't look identical to mine, if you've cleaned it up, it looks good. You have only one trig identity, or excuse me, one trig function. You have just sines or just cosines in your answer, and it looks clean. It's fine. Okay, so just make sure that you're cleaning it up. It looks better in the end than what you started with, and that you have a single trig function, just cosines, just sines, just cosines, just tangents, but you have a single trig function at the end.